I am delighted to introduce our November 2DCC webinar speaker, Judy Ji from MIT. And Judy is going to be talking about local microwave probe of excitonic excitations in a fractional Chern insulator. So Judy, whenever you're ready, please go ahead.
Thank you, Stephanie. Let me share my slides. So thank you for the organizers for inviting me. And today I would use this opportunity to introduce our recent work on local microwave probe. And yeah. So before I start going into the material systems that we probe, let me first introduce you a bit of our technique. So the technique is called microwave impedance microscopy. And from its name, it's microwave coming in onto a metallic tip. And so because the tip can confine electric field to a very small region, so usually on the scale of 50 nanometers. And so we measure the microwave reflected back from the tip because the tip can be screened by the sample. So if the sample is very metallic versus if the sample is very insulating, you have different reflections back onto the tip. So if you look at this response curve using finite element simulation, you will see that when the material is very insulating underneath the tip, a lot of microwave will penetrate through. And so you get the least signal from this green line. And then on the other hand, when you have a metallic system, then you will have a lot of back reflection due to the screening of the electric field from the tip. And so you will get the largest signal from the reflection. So you can understand this type of technique as a local measurement of conductivity. Of course, in the other channel, without going into too much detail today, this technique is also sensitive to local permittivity and other responses. And here is our electrical diagram. Without going into detail, this type of technique allows us to send microwave into the cryogenic systems. And so we have access to a wide range of material systems of interest. And then we also have the technique of very high sensitivity or signal to noise ratio readout. Okay, so this is my outline for today, and I would like to introduce how we use microwave local sensing to sense excitonic excitations, and also how we use it to study a fractional Chern insulator. A bit of a background of excitons. So excitons can be described by a process of photon absorption and generation. So there's some drink, and then so this person just had that drink, and that's a photon. So it gained some energy, and all of a sudden, the electron and hole just like split with each other, but then they are bonded. So this bonding is the Coulomb force. And so we call this type of system the electron hole pair as a exciton. Well, excitons have been repeatedly proven to be a great electronic test bed, especially in recent years in those 2D semiconductors like transition metal dichalcogenides. It is a part of it gives the possibility of making like photodetectors out of 2D materials. And then also it's like heterostructures give a lot of flexibility or possibility in creating those like LED, solar cells, and quantum emitters and more. So, but then we always had this question of whether we can use excitons as a quantum sensor. Well, we have seen many other quantum sensors like nitrogen vacancy. You have a single spin, you shine light because it has this type of like three energy level system. And then so you can first excite it and then use this energy splitting to measure the local magnetic field as a sensor. But exciton, on the other hand, it's very similar in a way that it also has like multiple energy levels. These are flat bands, and then so we have ways to control it. So then we went on the journey of like thinking, well, whether we can also make excitons into a local sensor. Well, in order to make excitons into local sensors, we first need to figure out how can we sense them locally at cryogenic temperatures, especially because of the high signal to noise ratio and other things. And we wanted to develop a protocol for how to use it to sense other things and then identify the operation mechanisms or the tuning knobs, like how can we change the sensitivity, how can we change its mechanism, and also develop a readout algorithm for that. Well, so then we started like building a new technique based on the microwave impedance microscopy, where we started coupling light onto the tip. As you can tell here, this is a lens-tipped fiber and it sends in focused light onto the tip. And this is a metallic tip that sends in and also collects the reflected microwave. And this technique allows us to now locally optically excite the material to form excitons. And after forming excitons, we locally use that metallic tip to sense how much conductivity change that exciton give us. So, as a comparison of how this technique can sense and how it compares to other techniques, it turns out to be very complementary. For example, in our case, it is very easy to go to very low temperatures because the microwave circuit is very compact and can be embedded into different types of cryogenic systems. It can reach 500 millikelvin, and actually recently even like 20 millikelvin in a dilution refrigerator and with a large magnetic field. And we have this advantage comparing to some like optically coupled STM measurements that it doesn't need metal contact, nor any like specific surface preparation of the sample because the microwave can penetrate through all types of like polymers and other insulating layers. So you can have encapsulation in your 2D material without a problem. And it has multiple channels for reading out both the phase and the intensity of the microwave reflectance. So after we developed and tested this optical coupling, we started looking at a monolayer molybdenum structure. So we know that the exciton fine structure in a monolayer TMD has different species. For example, you have A exciton and B exciton coming from the spin orbit splittings. You have the ground and excited state excitons, a bit like hydrogen atom, 1s, 2s, 3s. And you also have like bright and dark exciton depending on whether it's momentum direct or indirect. You have charged or neutral exciton depending on the electron doping. Those family of excitons in this material now become our test bed. So this is our result, and I will explain in detail of what this figure is describing. So the x-axis here, sorry, the axis label got cut off, is the excitation energy. So optical excitation energy here. And then the y-axis is the backgate voltage that we applied to this monolayer TMD to dope it. And then, so what we saw, the color map here, red means very conductive, And then blue means very insulating. And in between, it means like the conductivity is in between. So as you can see here from the response function, red means conductive. Okay, so in this figure, you can tell that there are specific regions where there were some like bendings downward of this blue region. Well, so what is that blue region? That is the band gap. So as we tune the gating or the doping, we first go through the conduction band and then the band gap, then the valence band. So the band gap gives a very insulating result. And then on top of that, at specific optical excitation energies, what we see are a bunch of other features. And those features turn out to be in good agreement with where those exciton species live in energy. So what A1S, B2S, B1S, A3S, and a bunch of trions. So we can compare our results with other near field scanning results of excitons at room temperature. So it has been achieved in Dmitry Basov's group in the SNOM measurement at room temperature before. And because we can go down to 1.5 Kelvin, so the advantage here is we can see the bandwidth of the exciton, which has to do with how it couples with phonon and relaxation mechanisms, is narrower. So if we want to get a more pristine, if you wish, excitons, then our technique now can see it at very low temperatures. Well, so after describing the sensing technique for excitons, we now can develop a protocol for using excitons to do the sensing. So excitons are always having this like recombination process. It's fate, right? Because like after excitation, it somehow has to relax back, or we call it recombination. And there are different types of recombination pathways. Sometimes it can give up its energy to a different free carrier, and then it can even knock that whole electron out of a barrier. And then so
Hey, Judy, I think maybe we lost you. Is anybody else here, Judy?
both.
Okay, great. Yeah, we lost you for a minute there, Judy. Maybe you could back up a little bit and repeat.
Oh, yeah, sure. Sorry for that.
Okay, thank you. No
So
problem.
where should I start with? Maybe the starting of this slide.
Yeah, that would be great.
Yeah,
Thank you so much.
Okay, great. Thanks. So we wanted to develop a protocol for exciton sensing. And so excitons have the fate to recombine after its excitation after some time. So then its recombination can either knock a hole out by giving up some energy to a different free carrier. And then this free carrier now has a lot of energy to go through some energy barriers. So then we call it OJ-assisted tunneling. On the other hand, it can also become trapped, like partially trapped. So hole become trapped, and then the electron becomes a free electron, and that can give rise to some photoconductivity. So then both processes will give us the so-called optically coupled MIM signal. So if you allow me 1 second, maybe I will try to switch to a different internet. I saw it was unstable connection again. 1 second. Okay. Yeah, I hope now it's better. So since both processes can give rise to the um, change in microwave reflectance signals, then we can tune the system parameters like electric field conductivity and permittivity, which can all affect the exciton recombination processes. And upon changing those parameters, we can expect changes to our readout. So then that just forms the protocol for our excitonic based sensing of local electrical parameters. And then we started identifying the operation mechanisms or the tuning knobs. And one of that is the carrier density. So we know that excitons can form trions or exciton polarons if there's like a, a pretty dense Fermi sea. And when exciton polarons form, the binding energy would change. And that's also what we saw in our measurements. So this is the measurement with different doping, and different doping changes the electron density. And when the electron density changes, or the carrier density changes because of the exciton and electron interaction, you see the binding energy here got extracted from the local measurement also changes. Similarly, when you changes electric field can also change the exciton binding energy by the so-called Stark effect. And then, so upon having this type of change, there is a E squared type of dependence of the exciton energy. So we call it the Stark shift. And notably, so this type of electric field dependence was observed at the boundary of two parts of the sample here. So one part is only encapsulated, the other part is on top of a graphite backgate. So then at the boundary, you will see the in-plane electric field from this like gating. And so that's the advantage of local measurement, because then you can really confine the probe to a very local region and see what is happening there. So the third thing we measured was as a function of dielectric environment, what happens? Well, as a function of dielectric screening, because if you have a nearby metal versus having a nearby insulator, there are different screenings. And this type of screening can also give rise to jumps of this binding energy of the exciton. And then so this is what we also observed. Okay, eventually we started developing this readout algorithm. So we used some deep neural networks as the trials because there were a lot of data, and there were 2D maps of 256 by 100 pixels in one map. So in this map, for example, that's 256 by 100 data points. And then we have a lot of like different optical excitation energies. And also we have different channels. So all in all, that's like we have a super high multi-dimensional data. And in order to process those data effectively, we just like started using some of those like machine learning based methods, and we were able to extract the local conductivity and permittivity, among other things, from the material. So you can tell here from light off and from excitonic excitation at different energies, we could see a sharp contrast among the different 2D scans. And also here, comparing the light off and light on, we see the photoconductivity distribution as well. So it's a powerful way of really use excitons to sense local properties. And especially, we know that local electric field is a bit harder to sense compared to local conductivity and permittivity. But here, upon just like simulating the Stark shift of the exciton, we have a good understanding also of the field locally. And we can compare that with some like simulations, and we found good correspondence between the measurement and the simulation. So that gives us hint that we can now use excitons as a local electrometry and also other electric field sensor. The conclusion here for this part, we sensed the excitons locally, we identified the operation mechanisms, and developed a protocol for exciton sensing, and eventually developed a radar algorithm. And all in all, that's our attempt to really use like those excitations in 2D materials as sensors and even quantum sensors to promote its applications. Okay, so I will proceed to part B of a different thing that we sense in a similar material system. And so that starts with the introduction or a recap to fractional quantum Hall effect. The integer quantum Hall effect describes when you put on 4 leads and you measure a two-dimensional electron gas subject to a large magnetic field, then what you see is at certain magnetic fields, the longitudinal conductivity or resistance becomes 0, and then your transverse conductivity or resistance becomes quantized to E squared over H. And so that's the integer quantum Hall effect. But then if you have a really large magnetic field, or in other words, if you have partial filling of your system with some non-perturbative Coulomb interactions among electrons, strong interactions, and low disorder, then what was first saying in 1982 was the fractional quantum Hall effect. You can see here as a function of magnetic field and how much Landau levels you are filling in. There are fractional fillings giving you a similar gap in the book. Basically, your longitudinal measurement gives a 0 resistance, and then your transverse conductivity or resistance is quantized. So that's the fractional quantum Hall effect. And when we talk about both the integer and fractional quantum Hall effect, the edge state is of great importance. The reason is this type of transport, usually they happen at edge state. The bulk is insulating. So we want to understand what the edge is doing and how the edge and the bulk are correlated. In the case of an integer quantum Hall effect, it's a bit simpler to understand the edge. Well, you have some confinement potential, you have some Landau levels, and that's the quantization giving rise to that transport result. And at the edge, because of that confinement potential, due to the sample edge or some other edges, those bands will bend up. And when those bands bend up or down, then if you draw a line for your Fermi energy, you will traverse different numbers of bands. In this specific case I draw, this is nu equals to 2, filling factor equals to 2, so 2 Landau levels are filled. And then you will then see 2 edge states. So this type of measurement have been done, and quantum Hall edge states have been locally resolved using SQUID. In the case of fractional quantum Hall effect, it's a little bit troublesome because of the strong electron-electron interactions. So theoretically, one can describe it as a Cairo-Lallinger liquid interaction, 1D interaction liquid, interacting liquid. Then more than that, it has a so-called particle hole symmetry. And the particle hole symmetry dictates that if you have a filling 2/3, so 2/3 of your Landau level is filled, but then it means that the particle hole symmetry just tells you this is equivalent to nu equals to 1/3 of hole filling. So electron filling of 2/3 equals to 1/3 filling of a hole. And then, so in that case, it won't directly be able to go back to nu equals to 0 or the outside. So it has to first go through a nu equals to 1, which is the nu equals to 0 for the whole level. And then it goes back to nu equals to 0. So that's just to say the edge is complicated and there have been multiple theoretical and experimental trials on that, and many theoretical models modeling different scenarios, different material system, and so on. So these are some of the examples without going into detail. Okay, so over the years, starting from the two-dimensional electron gas system, people have started like studying and manipulating those edge states. So one of such example is the magnetoplasma resonance study. And here you put on two leads and you measure the microwave, how it like goes through. And you see those like going in rounds, the plasmons. And the noise measurement showing that there are some charge neutral modes at the edge, some conduction stripe measurements by just like gating locally but measuring transport, and edge state interferometry. And that's what people claim to be the pathway to topological quantum computing. Because once you can start manipulating those edge states, you have anionic excitations where you can access, and those non-abelian anions were believed to be the major like source or pathway to realizing this advanced topological quantum computing without error correction. Well, then you may ask, like, can we just directly image the edge states? If we can directly image the edge state, we can directly get the bulk edge correspondence. We know what happens at the edge locally. Well, there are some technical difficulties. For example, those fractional states, they only appear at very low temperatures because the electron interaction has to be strong enough, the disorder has to be weak enough. And it has to happen at high magnetic fields for the normal cases of quantum well-based, two-dimensional electron gas, or 2D materials. And for requirements of the probe, we wanted spatial resolution, definitely. It has to be sensitive to the bulk and the edge and their differences. And also, ideally, we don't want direct electrical contact to it. Well, one is that those devices are always encapsulated. So like regular STM can be a little bit hard to directly like probe the surface because the surface is buried. But there's one type of system which is developed or discovered recently that free us from like really having to access a very high magnetic field. And such analogy happens in so-called the fractional Chern insulators. So the Chern insulator is an example first proposed by Houdin, where you can use a system with magnetization to really replace the external magnetic field to achieve quantum anomalous Hall effect. But in the case of partial filling and interaction, kind of naturally, but actually it was a lot of like theoretical effort for people to find this like fractional Chern insulator. And this fractional Chern insulator similarly has fractional states, but they don't need magnetic field. And one such realization at zero magnetic field is in the twisted system. So twisted molybdenum was recently determined as a fractional Chern insulator. First, in theory, Alan McDonald's group saw that in the valence bands of this moire twisted homobilayer transition metal dichalcogenides, you have such type of band structure in the moire unit cell. You can see that they have non-zero Chern numbers, or to say those bands carry non-trivial topology. And on top of that, these bands are pretty flat. So this would really drive us back to the case of a fractional quantum Hall effect. You have flat bands, and then you have non-trivial topology. So then later on, our collaborator at University of Washington, they observed the fractional Chern insulator in the twisted molybdenum telluride system. And here, the x-axis is the displacement field, the y-axis is the transport resistance. And then at low displacement fields, or to see when the two layers are hybridized with each other, then you have this fractional states signature coming out in their transport measurement. So in this system, we now have something which has a larger thermodynamic gap, which is 7 millieV. This is much, much larger than the gap of a normal fractional quantum Hall effect in a two-dimensional electron gas or graphene. And then it doesn't need us to apply magnetic field, and we can even see that state at around 3 Kelvin in twisted molybdenum telluride. So that gives us a great material system to study. But there's one more thing that we really needed to figure out, which is this sample is dual gated. You have a top metal gate, you have a graphite bottom gate, and both gates tune the doping and also the displacement field inside the sample, or to see how imbalanced are the charges on the top layer and the bottom layer. So upon tuning that, that's great. We have access to a full phase space of this twisted material. But on the other hand, the top gate would screen microwave because the top gate is metallic and metals would screen microwave. And then, so we utilized our finding in the first part of this talk that monolayer TMDs under excitonic excitations, they can have a large transparent region. So here at A exciton and B exciton excitation energies, so you see those like bluish colored region, which is very long and broad in doping. So that's to say, we can somehow make this top gate out of like a monolayer TMD material, and these materials can give us some like fancy transparent top gates with large transparency to microwave. And upon doing that, we get enough carrier density to tune the sample, but still very small mobility. Okay, so now we have these two parts together, the new technique and also the new material system, and we can tell what happens. So first, I will show some like transport results. And the transport result here from our collaborators group and Tingxing's group, as a function of the x-axis is the doping or filling factor. The y-axis is the displacement field. So one is what is the total charge carrier in these two layers. One is like what is the differential of these two layers. And then so we can tell that in this color map of resistance, there are certain regions in the middle. For example, here, certain regions in the middle where we have zero or vanishing rho xx or rxx. So, and then on the other hand, although I'm not showing it here, the edge or rho xy shows up as a quantized value. But that not only happens at nu equals to -1, but also happens at other fillings like nu equals to -2/3 or nu equals to -3/5. So these are the fractional states Well, this is the integer state. So that's the transport result, and we can compare with what we get using microwave. So this is what we observed. We saw that in the case of 1.5 Kelvin measurement, we have the yellowish region as like larger intensity, or to say more conductive. The purplish region, that means insulating. And so there, definitely we can see one insulating region. That insulating region is the quantum anomalous Hall effect. And we also saw this nu equals to minus 2/3 and nu equals to minus 3/5. So upon seeing all those things, it tells us that we can use microwave impedance microscopy. We park the tip in the bulk of the sample, and we can measure something very similar to transport. And so we also went to the larger filling regions, for example, next to minus 3/2, and see what happens there. And we can see a very fainted line over there. And that we believe is also giving us some hint and in some of correspondence with transport measurement. You can see this faint line here, and also some like optical pump probe measurements by other groups. But then the major thing we wanted to look into is the edge state, because we have this like capability of doing some sensor measurements. And so here I will introduce you to a bunch of like scanning images. So before doing that, I will first explain like the scan region and what is what in the figures. So the scan region is shown here. This is like a yellow rectangle. And then this blue dotted line, that's the flake edge. So the flake edge is horizontal. And then we also have an interface region without top gate. So that's the red dotted line. And then, so these two big metal-ish colored stuff, so that's the electrodes. So we have two electrodes connected to the sample. Okay, so then what we did was to scan in that scan region, and then we tune the top and bottom gate through the nu equals to -1 filling. Then what happens is as we move, well, this is a sample region. This is outside of the sample. We can tell that to begin with, it's pretty conductive everywhere on the sample. But gradually, when we went to filling nu equals to -1 over here, well, the bulk, so the inner, is dark now, but the outer is bright. So what that means is there is a conductive edge, but the bulk is insulating. And that is the observation of the integer quantum anomalous Hall edge state. Well, we went down to see how the fractional states behave. As you can tell, in the beginning, it's conductive everywhere. The bright color means conductive, 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 conductive. And eventually, when it approaches nu equals to -2/3, so this region, the edge here is conductive. This center is insulating again. So here we again saw the bulk edge correspondence. And then similar thing happens at nu equals to -3/5. And that marks the observation of the fractional Chern insulator edge states. One question that we really wanted to make sure was whether the edge that we saw is coming from some disorder in the sample, or is it really a consequence of the topological state? So what we did was to change the displacement field on the other axis. And then we see how this like imaging evolves. So then what we found was at a large displacement field, it's pretty dark everywhere, right? If there's this water, it's supposed to be also bright at the edge, but no, it's not bright at the edge anymore. But then as it evolves, it gradually becomes kind of spatially inhomogeneous and then keep evolving till here, the displacement field goes to zero, where the two layers are highly hybridized. The topology shows up, and here we can see this like inhomogeneity, or to say the edge being bright, the bulk being dark once again. And upon going to the other side, similar things happened. It's pretty symmetric of the displacement field that eventually just goes into a trivial insulator state. So this is observation of the topological phase transition. Well, of course, this type of samples have spatial inhomogeneities. So that's an inevitable issue for any of those like twisted or 2D samples. So then we kind of investigated like how much this water we had in the material. And it was not significant. It was only on the order of like 5% or something. So that just made it possible for us to see a pretty like global effect of the edge state. But still, what we saw near the topological phase transition, it is like how this like spatial map just messes up and then it becomes like very inhomogeneous. And that is a topic that we would love to look further into. We took a closer look at like what is the nature of the edge state. So what is we actually were measuring. Then this is a line cut of the edge state with different fillings. So what we found was when the filling approaches those like fractional states or those fractional fillings, then what happens was like the edge signal was even larger than the signal we got for a good metal. So it's to say not only the edge seemed to be screening the microwave very well, somehow it can enhance the microwave. Well, this enhancement was kind of explained by our theory collaborators from a different paper that they had in 2023 of edge magnetoplasma resonance. So in the microwave regime, you start to develop some like plasma or electron hole motions across the edge. And the plasma resonance, the first resonance would be going one round. The second resonance would be going two rounds, and then similar things like that. And so that explains some of the things of the edge signal. For example, the width of the edge is wider than what we expected by conductivity. But also, this edge state's magnetoplasma resonance actually carries more information of the fractional states, including the resonance frequency, encapsulating some or like carrying some information of the charge, whether it's a 1/3 charge or a 2/3 charge that tells us something. And also the characteristic width is on the order of the perimeter of the sample. So we can compare with some other previous studies using microwave impedance microscopy, including the observation of the quantum Hall edge states, quantum spin Hall, and quantum anomalous Hall edge states. And so we have included this into the family of the fractional anomalous Hall edge states. And then we are also in progress of developing some like new techniques for it, including embedding the sample into some like millimeter wave cavities, and then study the graphene and boron nitride. So this is one example, but in general, very high sensitivity conductivity modulation on the sample. So for the nature of the edge signal, if we assume a simple edge picture, then what we see is like you have a 2/3 edge state, and then we will have this type of observation from theory. But then we also saw that those edge states have certain deviations of their intensities from the model. And those deviations from the model, as you can tell, the -2/3 and 3/5 states, they don't look like having very large contrast in their intensities, can be in accordance with some of the early on theoretical arguments. For example, here, the K.N. Fisher-Purchinski picture was saying when you have a 2/3 state, then what happens is you have a nucleus to 1 and 1/3 edge state, and then they start hybridizing with each other. The scattering just made it into two eigenmodes of a neutral mode and a 2/3 state. And so this scattering induced process is going to make the edge magnetoplasma different. And so that difference is also encoded in our measurement. And because we can manipulate different domains, we also saw the coexistence of the 2/3 state and the 3/5 states. And this coexistence tells us that there is a chance we can really manipulate the fractional Chern insulating domains. And so, oops, let me go into the next slide. It's stuck. Okay, great. So I saw that the time is up. So I will directly go into the summary of this part. So besides using the optical coupled MIM, microwave impedance microscopy, to study excitonic excitations, we also went into the fractional state regime to facilitate the imaging of the fractional Chern insulator edge states here. And then we could also locally probe the bulk states. So now the bulk and the edge can both be probed by microwave. But there are a lot other open questions we wanted to solve. Can we see even denominator states, composite Fermi C, where what is the origin and the species of the magnetoplasmons that we're really seeing in our measurements? And that's to be studied for our. Okay, so I will finish with some acknowledgements to our collaborators, mentors, mentees. At Stanford University, this work was done in Professor Ziek's Shen's group, and with Mark Baber and Ben Thelman and Tom. And University of Washington, our sample was from our collaborator Xiaolong's group, and names for HBN, UC Berkeley, and Chou Chu for the sample, and our theory collaborators from UC Berkeley, Donghai, and Taiga. Thank you. That's the end of the talk.
Thank you so much. So we have some time for questions. So if you are online and want to ask a question, you can raise your hand, you can unmute and ask your question, or you can put it in the chat and Kelsey will keep an eye on the chat. Any questions from in person? Oh, I think some people had to leave actually in person. So are there any online questions?
If I may,
Yeah.
I have a question. Hi, thank you for a nice talk. In the first part of your lecture, you have mentioned using the AI or machine learning algorithm. So of course, in order to apply it to real data, you have to train it on something. So can you please explain how do you train it? What was the data that you can use to identify particular impedance or absorption or capacitance of the local materials properties?
Right. That's a really good question. So we did our training on the finite element simulation data. So then we looked into the dependence of just like different simulations with the material with different epsilon, the dielectric constant, and the conductivity and electric field, among other things. And then we just like simulated how the tip microwave interacts with the material to get a bunch of different results as a function of all those different quantities. And using that simulation data, we now have a whole data set to understand like what will happen when the material has certain property A, B, and C, what will happen in the microwave response. So then using that data set, we then started this like deep neural network identification of the local properties.
So just to clarify, that means that in principle, what you're doing is just the reverse engineering using the numerical simulation data, but there is no direct calibration of the numerical simulation data itself to prove that the simulation reproduces the physical object.
Yes, that's another good question. So if I can, okay, go back to the data. So this slide actually shows our effort um, of benchmarking. So I think you are talking about how can we benchmark the neural network generated result. And so we can do that through using different ways of extracting the excitonic parameters with some like known materials or known properties of the material, and we compare what we get to what that known result is. And we saw some like good correspondence there. I won't say we had a very systematic because for some of the results, where some of when the material is very conductive, we know what's the result gonna be. When the material is very insulating, we know what's the result gonna be. So that just like gives us some constraints of what will happen, and we compare what the neural network gets us to those, and then we could see good correspondence. Although it still doesn't mean that there's one-to-one correspondence, we can only say that it gives us some confidence that we are doing the right thing.
Thank you.
All right, we have time for maybe one more quick question. Jin, did you have one? Yeah, go ahead.
Yeah. So thanks, Judy, for this very nice talk. I think you showed it, but I just didn't quite catch it. You are using a TMD, monolayer TMD as a gate.
Yes.
And you have a sense for like how insulating it has to be in order to let the microwave through, but still, gates properly. What's
Yes.
the presumably, it doesn't have to be EMD. Anything with that level of conductivity could do it. Is that a correct assumption?
Yes, that is a correct assumption. So what we found for the TMD, of course, its conductivity is a pretty rapidly changing function of its doping. But then, so in this graph, so we would see in the specific case of using TMD, we can reach a pretty insulating regime of the 2D conductivity 10 to minus 7 or even lower than that for a certain range of doping that we needed. So that can be also sort of like seen in this figure.
That's around 10 mega ohm sheet resistance. Is that right?
Yeah.
That's sufficiently insulating for the microwave, but you're still gating okay. You're not getting like a lot of hysteresis or charge jumping, so on and so forth.
Right. So it's a pretty crappy gate. So definitely because the RC constant is very long. So in
Right.
order to use it, we really needed to tune it slowly. we use that as the slow axis because of this. But as long as we can do that, we can get rid of the hysteresis. So basically, it's not gonna work as good as a metal gate per se. And yes, your previous question, whether another material with a similar conductivity can also work, I think the answer is yes. We just utilize this TMD because we have characterized it and use a microwave, and we knew that it's gonna work.
Is it cleaner than some crappy oxide which conducts well? Because it is a 2D material, but it's not that defect free, right? I just wonder what is a better is better than a conventional material that just doesn't conduct so well.
Right. So actually we have thought a lot about like what is the best crappy material that can be used here. Uh, so so some people would use like a graphene layer and then they apply a magnetic field to drive it into the quantum Hall region, and that's pretty insulating. So that's also something that people can use. For the oxide that you mentioned, I guess. Yes, that's also worth trying. For the TMD, yes, there are a lot of like local defects. What we found from some of these measurements was that we didn't see too much like so-called charge puddles that create a lot of problem in the inhomogeneity of the gating profile in space, which was pretty good actually. But then so if you put it in air and oxidize it for some time, then it will become worse. So that's also what we found. For the other oxides, so if you have great candidates, like I would love to talk to you.
Thanks very much.
Thank you.
All right. Well, that takes us to the end of our time. So let's thank our speaker one more time for a great talk. So thank you so much for coming, Judy. We really appreciated it.